kind introduction. I am the person who has the responsibility of keeping you awake after lunch. So, we're gonna, if you don't mind, we're gonna do a small exercise. Okay. It's gonna be very simple. Raise your right hand if you have, in some point in life, heard about the term artificial intelligence. Good. How many of you have heard about the word generative AI in 2023? Okay. Raise your left hand if you have heard about the term predictive AI. So, I have been told by people that I've always assumed that people know the difference between generative AI and predictive AI, just making sure. So, back in 2019, we had this idea of developing predictive models that can look into the future. So, in particularly for hydroclimatic applications, trying to predict the water resource aspects from climatic data sets and trying to predict it so well that we can actually forecast the future. So that was the idea back then in 2019. It has obviously evolved over time. We had many challenges during the last 4 or 5 years while we were working on these topics, especially when it came to publication of our results. There is a challenge related to how people conceive artificial intelligence and how much they can trust these models. Okay, so that's when we decided to kind of evolve these models to explainable AI. So basically, not only being able to predict and forecast the future, but also explain how the models are predicting the future. So what is the physics going on behind the data sets that we are using to train these models using explainable AI? And then we had some very interesting research questions that we wanted to answer. And those are whether any kind of adaptation and mitigation measures that are implemented, are they really effective? And if they are effective, are they going to remain effective in the future? 30 years, 50 years, 70 years down the line, are they going to remain effective? So the way we answered those research questions is, again, we had to take the AI models that we had developed back then to the next step and use counterfactual AI. So counterfactual just means what-if scenarios. What if this was not implemented? What would have happened? So answering those questions. So with that introduction, let me start my talk about today, which is explainable and counterfactual AI for hydroclimatic analysis and forecasting. All right, so we heard the wonderful presentation from Dr. Wooten this morning about different climate projections, CMF5, CMF6, RCP, SSP scenarios, 4.5, 8.5. So how do we take that information, that rich information, and translate it to hydroclimatic insights? So our models use climatic data as one of the variables to train itself, in addition to different other variables which we call lags of the independent variable that we're trying to predict. I will try my best not to involve any math in today's talk, especially after lunch. That's not idea, right? So, how do we take that information and project the future of water resources? So we are going to use, as I said, or we have used predictive AI to try to translate the relationship between climatic factors and water resources, and use that relationship that the model learns to predict the future or forecast the future. However, since there was a rising concern about the transparency and explainability of these models, especially comes from hydrologists like, okay, how can we really trust these models? Can we actually trust the predictions that's coming out of these models? And are your models transparent? The transparency part is the easy part to answer. It's basically letting people know what kind of data sets we have used in our models to train them. So that's not a very difficult thing to illuminate. Okay. The explainability part is the most difficult thing, because if you have heard about AI, you must have heard about the term called black boxes. Okay, AI is referred to as black boxes, and we don't understand why it's predicting something. So we wanted to, that was the most difficult challenge, and we wanted to overcome that challenge. And the way we did that was finding a middle ground between predicted accuracy and explainability, because you cannot have both. There is always trade-offs. If you have a very, very simple model, those are extremely or highly explainable. And if you have a very, very complex model like a deep neural network where you have hundreds of thousands of neurons built together in several layers, those are extremely difficult to explain, like why the model is predicting something. So we took the middle ground. We know that models can be of different structures. So the structure that we chose was decision trees. Now, decision trees are very simple models. Just by itself, it cannot capture the complex relationship between climate and groundwater resources in this instance. So what we did was we bundled, hundreds of thousands of these small decision trees together, and then by doing that, we found that you can increase the predictive accuracies multifolds. However, since these are essentially decision trees built together, which are very simple models individually, right? So you have the capability to explain the small units that is used to build the entire big model, AI model that's actually predicting the type of variable that you're interested in. So what we did was we applied a post-hoc explanation layer on top of our ensemble of decision trees. That way, we found that when we applied it in practical world, and we tested that with historical data as well, that it doesn't only give you high prediction accuracies, but it also gives you some explanations that can be highly useful for stakeholders and decision makers. And obviously to give some relief to the users that these are not really black boxes. It's not that we do not know anything about these models. We actually know a lot of the thinking that goes behind these models and how it's coming to a conclusion about a certain prediction or a forecast. So, the first thing, predictive aspect. We have put so much effort into modeling the groundwater resources. In this particular case, we are modeling the groundwater levels, and this was published in 2021. We developed these models in 2020, and this was published in 2021 in the Environmental Research Letters, where we predicted the groundwater levels until the end of the century using CMIF5 data sets. That's what we used back then. So have we been successful so far in terms of our prediction accuracies? It turns out, and if you, I hit the wrong button, I'm sorry. If you see right here, we predicted two scenarios back in 2020. So that was left of the blue line that you see here, that was the historical part. and the right side of the blue line is the predicted or the forecasted part. So if you look right in this region here, back then we had predicted that the groundwater level would be somewhere in this critical stage 4 region. It might be a coincidence because climate scientists might tell you you cannot exactly pinpoint the days, but roughly given a certain period of time, you can say, okay, this should be in this particular range. Does anybody know what is the current stage that we are in right now?
4.
Look, we kind of predicted some of those scenarios, although we predicted that the groundwater level would have been lower in this particular case, which was kind of surprising. And also some of the reviewers, I remember, they questioned us because back then when we were trying to publish this paper, we were in the high ranges. So they asked, what is the reason why your model is actually predicting this drop here? All we could say back then is that we have cross-validated these models with historical data sets, and they produce about 90% accuracies. So that we're kind of limited to how we can tell about the future. Always there is some uncertainties when it comes to these predictions, and in our case it's about 90% accurate, or we can say with a confidence of 90% that these situations or these projections are probably going to be seen sometime in the future. So that was the predictive part. Right now we have more confidence in our models than we did back in 2020 or 2021 because of how it's playing out in the real world. However, what about the explainability part that I talked to you about? So, as I said, we apply some kind of post-hoc mechanisms that is based on game theory to understand why a model is predicting something. What we found was that when temperature increases in this particular, I'm talking about the Edwards Aquifer region only. So here we are looking at temperature data, Tmax data for the San Antonio region. We found that whenever the temperature increases beyond 30 degrees, approximately about 30 degrees Celsius, the soil moisture, which is represented by this color bar here, so the blue color represents low soil moisture, and the red ones are high soil moisture. So whenever temperature increases beyond 30 degrees Celsius, the soil moisture drops drastically. Okay? That's the first observation. And on this y-axis here, this is analogous to the groundwater level, whether it's going up or going down. So if it's going up, then it will be in the positive region. If it's going down, it will be in the negative region. So we see from this particular plot, temperature goes up, soil moisture goes down, groundwater drops. And from the plot up top here, where we have precipitation in millimeters, and the color bar in this case represents the evapotranspiration ET. What we found was that whenever the precipitation, or whenever we have those high precipitation events that are well known to do most of the recharge in groundwaters or in aquifers, what we found that a lot of the precipitation was going away as evapotranspiration. We were losing a lot of that because we see that in the high P region, the EP is also high, the red dots. Most of it is just red dots. So high precipitation, higher evapotranspiration, and so that we can correlate. So most of the high precipitation events are actually, we are losing some of it, okay, because of the high evapotranspiration. So a model, an AI model, which has no knowledge about the physics, can somehow understand how the temperature and precipitation is related to the soil moisture and evapotranspiration, and how all that translates to making a prediction about groundwater level or spring flows in some cases. I actually have some spring flow results as well, but that's the next part. So, do we have any questions so far before I move on to the next part?
Just one.
Yes.
Are these daily or
What time frame are
These are weekly, sir. Yes. What we found during our modeling, when we were developing our models, is that when we use daily data set, the noise is too much and the models tend to overfit the data, so we didn't want to overfit our models and make it memorize the data. We want our models to be as creative as possible, try to predict new scenarios that may come up, so it was not wise for us back then to use daily data set for training our models. Any other questions? All right. So the next step is the counterfactual AI that I talked to you about. It's basically answering questions like, what if there was no adaptation and mitigation measure? Okay. Raise your hands if you have heard about the adaptation and mitigation measures that are currently implemented in the software. Okay, so let me give you and honestly, I think Paul or Hakan would be a better person to explain the adaptation and mitigation measure, but I can give you a summary of what's in place. So basically there's the critical management plan, and then there's the physical plan, artificial storage recovery. So these are different mitigation plans that are implemented when the groundwater level of a stream flow is below a certain threshold that is defined in their guidebook. Did I get it right? Okay. Yeah, close enough. All right. That was the most difficult part for me. Okay. Anyway, because I'm not a hydrologist or a climate scientist, I'm a data scientist. I love looking at data sets and trying to establish relationships, looking at patterns, and trying to predict the future. I love predicting the future. I'm not one of those people that can be like, let's see, we'll see what the future holds. I have to predict the future. So now, the next research question that we came up with was whether these adaptation and mitigation plans that have been implemented in the Erebus Aquifer, and we know that the first instance of those adaptation and mitigation measures were implemented around 2006, give or take. So, do we have a way of saying for sure that those adaptation and mitigation strategies have been effective so far in terms of protecting the groundwater resources that's there, in terms of maintaining the groundwater levels and maintaining the stream flows? And the next research question was whether these implemented adaptation and mitigation strategies will remain effective in the future under a changing climate. And the way we found, the best way, or the shortest way to answer these two questions was using something called as counterfactual AI. So what if? Okay? So that brings me to the next slideshow. And this work, we're trying to get it published. It's in a preprint. If you want it, I can share this with you later on. But here is what, or how we developed the model, or how we kind of answer the research question. And in AI, it's all about how you ask the question, and that's the way the AI model is going to answer. So it's framing the question is very important in AI. So we know that 2006 here was the first instance when the implementation was done for adaptation and mitigation. That was the critical stage management plan. And if you're seeing these CS1, CS2, CS3, CS4, CS5, these are actually critical stages. That's part of the I forgot TCM.
CPM.
CPM. Yes, critical management plan. So what we did was we took the entire data set that we have, that was from the 1950s, all the way to 2023. And we distributed the data set into 3 different blocks. The first block was the data until 1990s. So from 1947, I believe, to 1989 was the data that we use to train the model. So we are training the model to look at or to understand the patterns between the independent and the dependent variables. Then we tested our model with the data from 1990s all the way to December 2005. Okay? What we found was the model was giving a good accuracy, and this is for spring flows. Okay, this is the minimum spring flow in Como springs. Okay, and we found that the model or the predictions from the model actually aligned very well with the observed values, and we saw that the R square is about 0.8. 1 is the highest, and if you have an R square of 1, that means it's a perfect model. Although from a data science point of view, we don't want to see an R square of 1 for training. For testing, it's wonderful. Most of the times, it's impossible to get if your data is very nonlinear, which in this case is. So we found that the R square was about 0.8. Then we used the same model that we used to test during this period to test during 2006 to 2023, the period when we knew that the adaptation and mitigation measures were in place. And look, the R squared dropped from 0.8 to 0.3. And what are we seeing here? The predicted values are always, or most of the times, lower than the observed values. So there are some significant difference between the observed and the predicted, and the only way to attribute that difference would be adaptation and mitigation, because all the other dynamic conditions we are including as input in our models. Okay? Similarly, if we summarize these two plots for the entire time period, this is the observed between 1990s and 2005, and this is the predicted. We see that the medians are well aligned, the ranges are kind of comparable to each other. However, this is during the period when adaptation and mitigation measures were in place. We see that the median for the predicted has dropped considerably. The lower range is much below the lower range that was observed during this period. So, to summarize, this just means that if the adaptation and mitigation measures were not implemented back in 2006, the spring flows would have been much lower than it has been observed between 2006 and 2023. Okay, the median would have been much lower, the highest spring flow would have been much lower, and the lowest spring flow would have been much lower. Okay? Now, the next question is whether these adaptation and mitigation strategies will remain effective in the future under climate change. Now, we heard about RCP and SSP scenarios from Dr. Wooten this morning. So this is what it translates to. We take those climatic projections, integrate them with our AI models, and try to predict the future of water resources. In this particular case, we are trying to predict the future of spring flows at the Como Springs. It's just an example. And what do we see? Between 2023 and 2099, these green lines are actually coming from the same model that has been trained on the entirety of the data. So, beginning from the 1950s all the way to 2023. And since it's a time series and it's using the lags of the dependent variables and the independent variables, so basically now has knowledge about these new adaptation and mitigation strategies that have been implemented. Okay, between 2006 and 2023, it has looked at all that data set, so it understands that it has been implemented, that's in place. Okay, so the green lines are coming from that model, which knows about the adaptation and mitigation strategy, and these red lines are coming from the old model that I showed to you in the last slide, which did not have any idea about this adaptation and mitigation strategy. So those models were trained prior to 2006, so with data until December 2005. We see that if the mitigation and adaptation measures were not in place, then again in the future, the spring flow would be much lower than it would be when the adaptation and mitigation measures are in fact in place. This is another way of representing that thought. This is for RCP 4.5 scenario. If you remember, for RCP 4.5, the heating is not as much in comparison to RCP 8.5 from Dr. Wooten's talk this morning. So we see that in both scenarios, in both the climate change scenarios, RCP 4.5 and 8.5, with adaptation and mitigation, the spring flows would be higher in comparison to without spring flows. Okay? And that seems to be intuitive, but from a practical standpoint, from an implementation standpoint, these are research questions that's extremely important to answer. Whether these strategies are effective and whether these will remain effective in the future. We actually did a literature review on different aquifers that have more or less similar or similar adaptation or mitigation strategies in place around the world. We looked at about 700 different aquifers. We did not find any quantitative evidence if those adaptation and mitigation strategies have been effective in those aquifers. So it's kind of the first time we're trying to quantify the actual benefits of these strategies. Okay, so key takeaways. First one, yes, we can actually apply AI. It's a shortcut, I understand. There might be some questions about the black box nature or trying to difficulties in trying to explain how the predictions are getting generated, but the truth is, what we are seeing with our models is that these predictive AI models that we have developed are actually accurate, and based on the recent data sets that we have received, it seems like they have been doing a pretty good job in terms of the prediction accuracies. And when you add these post-hoc explanation methods on top of the predictive AI models, it actually increases the explainability and transparency of these models. It helps us understand the physics that the model is actually seeing that's resulting in the predictions or the end outcomes from the model. And counterfactual, or what if AI can help you make practical decisions, whether adaptation and mitigation strategies are effective, whether they will remain effective. If not, then what else can we do about it? So, and that's what we do. We just provide the information. We don't impact the end outcome in this decision. That's up to the stakeholders. But we try to provide all the information that might be helpful in the decision-making process. And I am a physics person. I love physics. I have nothing against physical models. But what I have seen is, based on my years of experience, is sometimes it's the shortcut way to get good accuracy, prediction accuracy, without having to put in the time and effort to develop very complex physical models. So these can be done with artificial intelligence, especially explainable artificial intelligence and counterfactual artificial intelligence. You can overcome some of the problems that's, or the challenges that's typically associated with mechanistic models. So these are some of the recent publications that we have that's relevant to this particular topic that I spoke to you about today. One of them is a preprint. We're trying to get that published in a high-impact journal. But if you want to read any of our papers, you can go on Google Scholar and find those items. If you don't have access to them, please shoot an email to me. I will be more than happy to share the prints with you. So with that, I would like to thank you all for your attention, and I'm extremely thankful to the Edwards Aquifer and the South Central Climate Adaptation Science Center for supporting this research. So thank you, and have a wonderful day.
questions? This one.
Predicted now. Okay, so we say we're going to change these mitigation strategies. What do you feel about the predict? If we change the mitigation strategies, what about the predictability of your AI models? Do you anticipate that having pretty good predictability?
Well, AI is not a magic capsule. It's basically a very sophisticated branch of math, right? And the way we optimize these AI models is using data sets. In this particular case, we were very fortunate to have a long period of data set that we received from the Debaditya, and from other public repositories for climatic factors, downscale data from Adrian. So, to answer your question, let's say, a hypothetical scenario, some aquifer somewhere decides to change their adaptation and mitigation strategy. Would we be able to predict what would be the impact of that? Well, the short answer is we will have to wait until we collect a sufficient amount of data after that has been implemented. Then we will have to train those models on the new data as well as the old data to answer your question. So we cannot say from day one whether strategy is effective or not.
So you need, for the Edwards itself, if there was a model that changed somewhere else, it would take X number of years to get the data to see how it might apply to the Edwards. Is this sort of what you're saying?
Yes, we would need sufficient data set to be able to say for sure how effective certain change is. Unless you develop some kind of physical models to generate synthetic data set with physical models, and there's a whole branch of research that combines physical models with artificial intelligence. And basically, in those cases, physical models are used to generate synthetic data sets that we would probably expect, and then train AI models on those synthetic data sets. We can answer that, but it's not going to be based on ground truth. Obviously, it's going to be based on synthetic data.
So that's where you put those two together and try to. There's potential there to predict.
Of course, yeah. There's a lot of potential combining physical models and artificial intelligence. We also have Dr. Ali Mirchi at Oklahoma State University, who works on the physical side of things, like developing those physical models. Dr. Bashal here also works or has good knowledge about physical models, so I know how to use those data sets using AI, so that's my expertise. But there is a huge potential there. I don't know, did that answer your question?
Yes, you certainly did.
Yes.
I was quite impressed with the discrepancy you showed between the model and the observed data post-2006.
Yes.
Were the adaptation measures, the conservation measures, implemented over a period of time, or were they all pretty much implemented right around 2006? And if they were implemented over time, and if there have been any additional measures put in place since then, does that show up in your data?
Yes, actually, we know for sure when the critical management plan was implemented. That was around the 2006 timeframe. But then the other programs like FISBO, the artificial storage recovery, these are programs that have come up over a period of time after 2006. I don't have the exact information when they began implementing. And then there were, I believe, some adaptation and mitigation strategies that were implemented by SAS, the San Antonio Water Systems. We don't actually have a solid time frame, but here's what we see with the data. And this is really impressive. You see this particular time frame when the predicted is actually below the observed values. But look here, the critical stage was not even implemented, because critical stage is, it kicks off at this level, right? But what happens above it? Why are we predicted below the observed in this time frame? And that's what we are speculating. We're speculating that's when the other adaptation and mitigation measures that have been implemented by agencies like SAS, that's the time frame when it became effective. So that's what we're anticipating.
So how do you account for, in your modeling, the situation where San Antonio water system is storing part of its Edwards allocation in the groundwater storage and then bringing it back out when other people are going into stage 4? How do you account for that as far as your modeling?
Yeah, wonderful question. The answer to that, the short answer is we implicitly model those things by using the lags. But in the future, we would really love to implement those factors explicitly if we have enough data set and information about exactly when those measures went in effect and how much. For example, the critical management plan is very straightforward. If the groundwater level and the spring flows drop below a certain threshold, the pumping restriction will be X percentage, right? So if we have that kind of solid information about the other measures that's being implemented by other stakeholders across the state, across the city, we would be able to model those things explicitly rather than implicitly. Right now, we are depending on the lags that we're providing to the models to kind of tell us answers to those questions that you're just asking.
Yes, thank you very much. A very interesting presentation, Dr. Charkraborty.
Yeah.
If you could return to the plots we just looked at of Comal Spring. Yes, that's the one where you were pointing out that perhaps something else was going on that affected the actuals. I think out around the 2020 timeframe, maybe slightly before that. Let me make sure I'm looking at the right color. One of them is a darker blue than the other.
So the blue is predicted and the black lines are the observed values.
Okay. What I was wondering if from what you have seen or from what you know about the Edwards Aquifer, what is the lag between the measures that are taken when something enters critical stage 1 and how prolonged or how persistent are those effects on the discharge at Comal Springs? Can anything be inferred from, yes, certainly perhaps from the observed, but do you think it's also incorporated into a model that includes data after these measures were implemented?
Yeah, great question. So basically the way we tackle that is we generate all the different lags that could be possible, that are realistic lags. And we provide all those lags to the model and let the model choose for itself which lags are the most predicted in terms of, predicting the groundwater levels, spring flows, whatever it is. We can change the independent variables, but we have a very modular framework that we have been developing very diligently over the past 4 years, 5 years. So basically, we have a very robotic approach. We have all the sets of lags that we can produce to the models, and we let the models choose for itself what is best in terms of increasing the predicted accuracy. So basically what we're trying to do is we have an error curve that's predicting the difference, that's modeling the difference between the observed and the predicted, and our goal during the training phase is to optimize that error curve or to find a minima that is very close to the global minima. That's what we're trying to achieve from a mathematical standpoint. And the lags, including which lags are most appropriate for predicting the future, we let the AI model decide for itself. Now for spring flows, it might be the first 2 lags, which is the week before and the week prior to that. or for groundwater levels, it could be the first 3 lags. So it kind of depends on the type of variable that we're trying to model. We do not force that information on the model, but rather we give the freedom to the model to choose those lags for itself in terms of reducing the error function.
May I ask a follow-up? And this is, of course, an unfair question. I know that this is taking a very lumped approach because, you're looking at spring discharge, and that's sort of a lump thing. But of course, the Edwards Aquifer, things are varying across it. So certainly, when you implement a restriction under a critical stage 1, and you do it in a spatially uniform manner, most likely for everything that's within the auspices of the Edwards Aquifer Authority. Some effects in the West, let's say, their effects on spring flow will be delayed versus those that take place more closer, at least in terms of transport time or suite of groundwater transport times to the springs. What sort of, and maybe this is an unfair question, it is, what sort of difference in lags between actions taken in the West and actions taken closer to the springs are seen?
Well, again, those are aspects that we're modeling implicitly based on the data that we have access to. So the data set that we have between 2006 and, so basically if the objective here is to be able to predict the future, so 2023 all the way until the end of the 21st century. So at that instance, we are going to train our model, and if the objective is to be able to predict with the adaptation and mitigation strategies in place, then we are going to train the model with the entirety of the data, which is available until 2023. And all those factors that you're talking about, like the lagged effects and the decisions taking place in the West versus the impacts from the East, we are finding that the models are learning that implicitly from the data sets that we have access to. So the lags we have provided, the model chooses those lags by itself. I'm sure if we have a code that gives us the lag back, the ones that it chose, that it had chosen for making the predictions, we can have a small, or we can develop a small code like that will tell us the lag exactly, but we were not very interested at that point. We are interested now to get the answers to the questions that you're asking, so maybe we're gonna develop that part of code. But so far, we had that inbuilt into the AI model, and we didn't ask it, hey, what lags did you choose? So I'm pretty sure it knows. So if we ask it, it will give us the answer. So we can stay in contact, and we can let you know what lags were the most appropriate for Como Springs, for J17 groundwater levels, or for San Marcos. We didn't include San Marcos because the variability is very predictable in nature, and we have those models. We included some data for J17 and Como in this presentation. Any other questions? Yes.
If I can add just a little bit to that, because I'm not the brightest bulb on the string of lights. It takes me a while to kind of get my head around this. And one of the reasons is, so these critical period management components are not actively incorporated into the model. There's no pumping component in there. So it's just responding to that a little bit. And I think one of the questions that I have, and I think Dr. Charkraborty has answered this quite a bit, is, well, there's so many other factors going on. It's sort of hard to do. It's like we're training on this data set in which we have good control over the critical period management stages, but we don't have good control over what alternative water sources are coming online. There's a sort of a Vista Ridge sort of time frame and sort of these alternative things. So the actual demand on pumping for particular temperature and precipitation regimes are changing as we're going forward. Similarly, it's focused on San Antonio pool conditions primarily, so we're not even trying to incorporate anything out in the Uvalde pool. We're sort of that, so it's a disconnect in that sense. and it's geared right now towards San Antonio airport conditions, which are reasonably relevant, but ideally we like to have a more spatial representation of the conditions, and I think that's essentially where we're going in the next phase is can we add a more spatially representative model to the system so that the components can reflect some of those factors that you're talking about, like, well, how does Medina County component influence that a little bit more? What's the relative contribution of the Medina County component to, say, J17 levels or canal spring flows? That makes sense.
Yeah, that was a very high wattage response, thank you.
And also, the reason why we do not include pumping in the modeling aspect is because the pumping data is restricted between 2000 and 2023, 2023. So basically, if we use the pumping data set, we are going to lose about 50 years of data set that we have for the groundwater levels or the spring flows. So that was a very hard choice to make, whether to include pumping in the modeling. But since we're including the lags, the assumption behind it is whatever pumping trends happen in the past is going to carry forward in the future before the adaptation and mitigation measure, of course. So that was the assumption, but since we're including the lags, all those other impacts of pumping or land use and land cover changes over time, these are all implicitly modeled from the data set that we have.
So this is more like a follow-up with Rachel's questions and also Paul's comments and answers about, so like the training data you use is like pre-1990, and then we all know that the management of water resources, especially in San Antonio, is dramatically different, especially post the EAA, and then the ASR or Vista-Ridge, those are just two of the practices, but there are many more, water transfer projects or desalination, all those. So you talk about a lot of these decision trees. So I was wondering, like, if there's a way of implementing some of the decision trees with the with practitioners and largely all these management practices. I think there are enough data being collected for many of these practices. And
Yes.
that would probably be more meaningful, especially when we predict the future with the population growth and also the conservation practices and also many potential projects to solve the water shortage problem.
Absolutely. No model is perfect, right? And that's why it evolves over time. So first you came up with Sigma 3, then Sigma 5, then Sigma 6. So it's a constant evolution over time. And if we have that kind of information, that kind of data set that are using which we can actually explicitly model these minute details that you all are talking about, then that would be fantastic. So of course, we are looking forward to collaborate on projects or finding ways to improve our models because no model is perfect and there is always scope for improvement in the future. What we're doing right now, the next steps for my research group is to be able to replicate this work with the CMIP 6 generation of climate change. And then as Paul talked about, that we're trying to get a very spatial representation of these changes. So in that case, we are going to use the recharge data that we have. Of course, it's synthetic data. It's not ground truth. We're going to use that, and we're going to use the groundwater levels and the spring flows that we are predicting as the inputs to predict the recharge so that we have very special representation. And then we can do the same things about predicting the future of recharge using the same principles or similar models that we have used for groundwater prediction, so spring flow predictions.
Well, thank you very much, Dr. Charkraborty. I appreciate it.